All right, so picking off from before, we were looking at this idea of starting with one of these cute little graphs. So if we have this nice little graph with 4 vertices, we obviously can easily construct the adjacency matrix for it. We can then compute this matrix A2, which is then going to keep track of all of these paths of length 2. With a little bit of zhuzhing, we could actually compute A3, which we had to do a little bit more effort with, but we can easily do that here too because the thing is not overly complicated, even though I obviously am still going to mess up along the way, but we can easily do this. So what we want to do is we want to begin kind of packaging this all together. So we have kind of our initial theorem statement, which is going to say that if you give me one of these adjacency matrices, then the number of different paths of length R is simply going to be that ijth entry in this matrix AR. So it would be paths that start at I and end at J. It's exactly the game we were just playing, is that if I want to look at A3, that's going to talk about paths of length 3 that are going to start at the I row and compare it to the J column. So that's going to be connected to node I and node J, depending on how you label those things. And if you give them cool names, you'll obviously have to modify those things a little bit. So there's obviously a bunch of questions that are then going to come into play. The first thing is that we need to know is how we're actually going to construct this adjacency matrix. That's actually really, really easy to do. So if you maybe automatically want to store the graph like that, you just create this nice big adjacency matrix. If you have a dictionary representation of that thing, it's obviously really easy to build the matrix out of that. That's not really a big question at all. The big questions that do come into play is it's great and dandy to start talking about having this matrix AN and talking about paths of length N, but how do we actually compute that efficiently rather than having to count up all of those things, because counting paths is really, really hard. I also want to think about what happens when that A becomes really, really big, and that's going to become even worse. If you have some network that has 10,000 nodes on it, and I want to begin talking about paths of length 500, that's just a tree waiting to blow up in front of you. Luckily for us, this actually is not so terrible. Well, there are some inefficiencies, but it's not super duper awful. And we're actually going to lean on that somewhat suggestive notation that I had before, which is to make use of multiplication of these cute little things and the inability to erase to actually compute these various powers of these adjacency matrices. So same starting place. So I'm going to have my matrix A, which is this nice little 4x4 matrix. That first game we had was to compute A2, which was chatting about paths of length 2. So I suggestively wrote this as an A squared, which should then look like A times A. And that's exactly how I'm going to compute this thing. I'm going to take one copy of that adjacency matrix, and I'm going to multiply it by another copy of that adjacency matrix. If you've seen matrix multiplication before, you know that there's some kind of crazy twistingness that's going to happen. If it's new to you, we'll walk through this nice little example of it, and that'll actually springboard us into a really nice little bit of code that actually does multiplication. So we'll jump into it. So when I do matrix multiplication, what's going to happen is that I'm basically going to have a really big outer for loop that's going to cycle through the rows of my first matrix. So you're going to think about grabbing, let's say, one of those particular rows. Then you're going to have an inner for loop that's going to cycle through the columns of the second matrix. So let's say we grab that one. So we have an outer for loop, now an inner for loop. Once you have those two things, so I have that kind of blue list of 1, 1, 0, 1, and I have this green list of 0, 1, 1, 0, what we're going to do is kind of this cute little twisty multiplication. Basically, what's going to happen is that I have my first list of 1, 1, 0, 1, and I'm going to have my second list, which is 0, 1, 1, 0. And what I want to do is I want to combine those two terms together. So 1 and 0 is going to multiply to make a 0. 1 and 1 is going to multiply to make a 1. 0 and 1 is going to multiply to make a 1. And 1 and 0 is going to, oops, the other one I totally lied. 0 and 1 is going to multiply to make a 0. 1 and 0 is going to multiply to make a 0. And then you're going to add all of those terms up, which is going to ultimately give me a 1 in that particular cell. That 1 emerged from that third row and that first column. So we essentially had that node of what, 2, comparing it with node 0. And that's then going to correspond to exactly that little entry in my final matrix A2. So I tried to keep these things kind of color coordinated so you can kind of see the twisty multiplication. So you have the blue 1 multiplied by the green 0, so the first terms on each of those lists. Then you have the blue 1 multiplied by the green 1, so the second terms in each of those two lists. Then the blue 0 and the green 1, so the third terms. And then lastly, the blue 1 and the green 0, which is then the fourth terms in each of those lists. So you're going to see that you're going to have 4 little multiplications that are going to take shape, and then you do 3 little additions to combine them all, and that ultimately resulted in that little 1 right there. Through symmetry, you have the exact same thing up in that top right corner of this thing, and that would have emerged from taking the very first row and then combining it with the third column, and that would have created that little piece up there. So obviously there's a little bit of efficiencies that we can start to think about is that, well, if we have similarities between the A and the A, obviously if I build up half of this thing, I can just do a cute little copy and paste. But for right now, we're just going to build this up as this big kind of nested for loop structure. So if you want to, you can go through a few of the other scenarios. Obviously, if you wanted to take the bottom row and let's say that last column, that would just be that term right there. So you'd stack the zeros, stack the ones, stack the ones, stack the zeros. You get 0 plus 1 plus 1 plus 0, which is then going to add up to 2, which is exactly this little bottom right corner. Hopefully in the back of your head, there's also just some kind of bit work that's going on, kind of screaming at you, being like, there's a lot of kind of overkill happening here, which there is. And there's actually going to be a lot of other ways that we can actually poke into this a little bit farther. This is keeping track of exact number of paths, but maybe I just want to know if a path exists. So then we can start using some exclusive ORs and some ands and things like that to do the arithmetic just a bit faster. What I want to do is I want to step back and think a little bit about how many multiplications and additions had to occur for just this simple multiplication of A against itself. So A was a 4x4 matrix. So when I multiplied it by another 4x4 matrix, i.e. another copy of A, you can see that the result was going to be this nice little 4x4 matrix, this A squared. It total has, what, 16 things then. So we have 4, 4, 4, and 4. In each of those 16 little cells, you can actually see that we had to do 4 total multiplications. So if I'm keeping track of the number of multiplications that I had to do, well, the total number of cells that exist inside of A squared was 4 times 4. To construct each of those things, I had to do 4 more little multiplications. That is, there's 1, 2, 3, 4, and that existed in 16 different locations. So the total number of multiplications that we had to do in order to construct A squared was 4 cubed. That 4 connected to how many nodes we happen to have on this particular graph. So if I change the 4 to 10, well, then the number of multiplications that I would have to do would then become 10 times 10 times 10, or 10 cubed. In general, if A is an n by n matrix, the number of multiplications is then going to be n times n times n, or n cubed. So there's a lot of stuff going on. If I wanted to think about how many additions I had to do, well, it's basically going to be the same. There's still 4 times 4 entries. I just have 1 fewer addition because there's only 3 additions that had to occur in there. So I have 3 plus signs in each of those little cells. So it's 4 times 4 times 3, or 4 squared times 3, which if you n-ify it, then it's just going to become n times n times n minus 1, which whatever is close enough to n cubed. So that's kind of the chat about the efficiency of computing these kind of multiplications of 2 of these matrices. The official little algorithm for it is the following, and I kind of tried to allude to it a bit as we were running through this. Big picture when we do this multiplication, let's go here, look at this one, it's a little bit less cluttered, is that we are going to have a big for loop that's going to cycle through the first rows of that kind of blue, that left matrix. Then we're going to have an inner for loop that's then going to cycle through the columns of the second matrix. Then there's actually going to be a third way inner for loop that's going to cycle through those 2 little lists and do that kind of twisty multiplication. This kind of terrible game that I played up here was really just another for loop that's going across the length of that kind of blue thing and that green thing. So that's exactly what the big multiplication structure is then going to look like. So it's a big outer for loop, which is going to cycle through the rows of my first matrix. So here I've left things somewhat general. So I'm going to claim that that first matrix has m rows. Then I'm going to have this second little for loop, which is going to go through these columns of my second matrix, which is going to have n columns. If it helps, just think about this as all being square. So they're all just 10 by 10 or 20 by 20 or whatever consistency. Technically, you can change them up a little bit. The only thing that's required is that when I do this twisty multiplication, that blue thing and the green thing, they had to have the same length. If those lengths are off, then this whole thing blows up. And that length I'm going to refer to as a nice little Q. So that's going to be my last inner for loop, is that we're going to cycle through those Q entries of each of those two little lists. I'm then going to do this twisty multiplication. So take the first terms in each of those lists, take the second terms in each of those lists, take the third terms, take the fourth terms, and take however many more they happen to have. Make sure they obviously have the same number of them. Do the multiplication of terms, and then constantly add them all back together afterwards. So that's going to be stored in our new little result, which I'm calling C. So I'm going to constantly update the ij term of C by adding on the next thing. So basically it's going to be initialized as 0. Then you're going to add on the result of the first terms multiplied together, store that in Cij. Then you're going to add on the results of the second two things multiplied together. So update your Cij. Then you're going to do the third terms, multiply them together, update your Cij. And then you're going to take the fourth terms or however many more you need, multiply those together, and then update your Cij afterwards. And that's it. So it looks pretty tidy, except for it has obviously 3 nested for loops, but it does really kind of poke into this idea that its runtime is going to be taking about big O of n cubed, and that's going to be keeping track of the number of multiplications that we have to do. Later, we can start chatting about how expensive multiplication actually is. For small little numbers, it's obviously not very expensive, but if these numbers start to get really, really big, then doing n cubed multiplications becomes a little bit less pleasant if your numbers are truly massive. So I'm going to leave this as it's going to take about big O of n cubed number of multiplications as well as number of additions. However you choose to do those operations may modify things just a little bit, but that's kind of the game that we get to play. And we're pretty close to optimal. So it's both awesome and slightly unawesome. There are technically other ways that you can do matrix multiplication that would use slightly fewer multiplications, but just a bit less. So ours runs in n cubed. You can technically drop that 3 to about a 2.6-ish or so, and you can get some extra efficiencies out of that as well. But not tremendous gains. You can dip it down just a little bit more. It's still running in obviously polynomial time, so it's not super awful, but it's pretty big once you have n be 10,000 or 10 million or 10 billion. That's a lot of operations that it's going to have to do all this kind of twisty stuff. What's also somewhat unfortunate about it is that I can't really offload things very easily. I do need to know kind of the entirety of A to multiply A by itself. And that I can't just be like, okay, split this, model A, go and do this thing over here, and then other things go do that over there. And then at the end, we'll kind of merge them up. That doesn't necessarily work so well in multiplication of these things. We have to do them all together. So we can't really get rid of some of the storage issues and things like that. Obviously, if I'm just computing A squared, I could do just the top right corner and then copy and paste that down. So it would dip this just a little bit. Basically, I had to do half as many operations, but it's still going to be running about big O of n cubed. All right, so I'll probably pause it there. I'm going to jump into a Python implementation of this and play around with that a little bit, and then we'll push this a little bit farther.